Hi, aloha everyone. Thanks for being here today. My name is Dan Mikros, and for the last 8 years, I've researched a litany of arthropod-borne pathogens from West Nile virus, Lyme disease, to Zika, and ultimately to rapid ʻōhiʻa death, which I've worked on for the last 5 years within the rapid ʻōhiʻa death entomology lab, and the last 2 years in the Hilo TCBES program with my advisor, Patrick Hart, and committee members, Ryan Roy and Kyle Roy. Rapid ʻōhiʻa death, or ROD, is a major concern of citizens and scientists alike. And by far, the most common question I get asked is, what can we do to practically help battle this novel invasive pathogen and help protect our delicate island ecosystem? And today, I'm excited to share some of my research that I hope will contribute to answering that question. As many of you probably know, ROD has devastated forests on Hawaiʻi Island since the mid-2010s and is arguably one of the most alarming ecological threats to the archipelago. However, more varied management strategies are still crucially needed. ROD is actually a novel disease complex caused by 2 fungal forest pathogens, Ceratocystis ʻōhiʻa and Ceratocystis ʻōhiʻa, both of which colonize the xylem and cut off the water supply as it infests the tree's vascular tissue, ultimately causing the rapid characteristic crown wilting and death that we all too commonly see. While both pathogens share pretty similar pathology, Ceratocystis ʻōhiʻa has been shown to be both far more virulent and prevalent throughout the islands than ʻōhiʻa. As of 2020, ROD is estimated to have killed over 1 million trees and affected 30% of the ʻōhiʻa forests on Hawaiʻi Island alone, with total mortality as high as 95% in some long-term laboratory plots. As the ʻōhiʻa is a cultural, ecological, and economic cornerstone to the islands, its decimation is likely to incur extensive repercussions. The iconic ʻōhiʻa is the most abundant and ubiquitous tree in Hawaiʻi and serves as an endemic ecosystem engineer, foundation, keystone, and pioneer species, which provides a myriad of vital environmental services. For instance, it is one of the first species to colonize new lava flows, setting the stage for future soil development and forest succession. ʻōhiʻa are also critical to the creation and protection of Hawaii's watersheds and provide critical habitat to truly innumerable other flora and fauna species, many of which are endangered. Just as it's rooted in the land, the ʻōhiʻa is deeply rooted in the history and traditions of the Hawaiian people, and every component is utilized for a diverse array of cultural practices. Hawaiian chants and stories are filled with references to the tree's beauty and deeper significance. It is often used to convey core cultural values and is regarded as the physical manifestation of multiple Hawaiian deities. The wood of the ʻōhiʻa is prized in the construction of ceremonial structures and statues, while the shoots, roots, and lehua blossoms are a mainstay of hula rituals, medicinal treatments, and other spiritual practices. In this way, ROD poses a multifaceted threat, not just to Hawaii's ecosystems, but to the Hawaiian culture itself. As the threat of ROD continues to loom, identification of effective management strategies is of critical importance. However, the lack of clarity surrounding the significance of each possible vector pathway has pretty significantly limited our ability to act proactively. ROD's primary vectors are suspected to include Ambrosia beetles, ungulates, weather events, and human activity. However, the rates of infection due to each are still unknown. Of particular concern are the Ambrosia beetles, of which there are 4 invasive species associated with the ʻōhiʻa and ROD. And these include Xyloborus ferruginous, Xyloborus saxonii, Xyloborus perforans, and Xyloborus affinis. And Ambrosia beetles like these have a haplodiploid sex determination system, where males develop from unfertilized haploid eggs and females from fertilized diploid eggs. And females will typically mate with sibling males before emerging from the natal gallery. Because of this, invasive populations can be established by a single founder's female, contributing to beetles being extremely common threats to forest health globally. These Ambrosia beetles brood within the tree to establish their breeding galleries and propagate their symbiotic Ambrosia fungi on which they feed. In doing so, they produce a boring dust referred to as frass, which can contain viable rod inoculum when excreted from infected trees. And this is thought to be the primary mechanism by which inoculum enters the environment, which can then be picked up and transported by any of the other supposed vectors. Additionally, beetles leaving an infected host have been confirmed to carry rod inoculum on their bodies and have the capacity to directly infect healthy trees as well. Because of this, these beetles are a primary target for potential intervention actions, but are so widespread and pervasive that developing effective methods to control them poses pretty significant challenges. Currently, the only widely endorsed ROD management recommendation is to fell and tarp infected trees with the goal of physically isolating beetles and the inoculum they produce from the environment. And here we see the typical tarping progression. However, tarping has limitations that can make it not broadly applicable. This strategy can often be cost and labor prohibitive and particularly difficult to apply at large scales due to tree size, number, location, or proximity to healthy trees and waterways. It can also simply be physically infeasible due to the rugged terrain common throughout Hawaii, contribute to increased plastic litter in the environment, and create mosquito breeding habitat. Most importantly, directly address inoculum production as the beetles continue to infest the wood within the tarp. Another project I participated in with the ROD-Ent lab showed that while tarping did reduce beetle emergence, it did not reduce new beetle galleries within the tarp, and thereby potentially the amount of frass being produced. In this way, if the tarp degrades or over time or is otherwise compromised, that inoculum can again be exposed to the broader environment. Alternatively, the application of superficial insecticide has been examined, but was shown to only reduce new beetle attacks for a very limited duration. More so, such insecticides can also be impractical for landscape level use due to their high cost and potentially detrimental effects on non-target species. On the other hand, non-toxic semiochemical repellents are used in the control of other bark beetle species and may be useful in regards to ROD. Ambrosia beetles rely on the olfactory perception of volatile organic compounds for behaviors such as host selection and mating. And this is a system we can potentially exploit to manipulate beetle behavior in the field. One such compound is verbenone, which is an anti-aggregation pheromone that inhibits attraction by indicating a degrading or otherwise unsuitable host tree. And this compound has been made commercially available by the company Iskatech as the product SPLAT Verb. And here, SPLAT stands for Specialized Pheromone Lure Application Technology, which is a wax-like matrix that can be applied directly to trees that releases volatiles over time. And we can see on the little wood square here, the dollop of paste is the actual repellent medium that we're talking about. SPLAT Verb only contains verbenone, but Iskatech has also recently developed a secondary formulation called SPLAT Beetle Guard, which also incorporates the compound methylsalicylate. And methylsalicylate is another semiochemical that is released from tree leaf tissues that is associated with systemic acquired resistance, this being a state of heightened immune defensive pathogens exhibited by trees. Methylsalicylate has been shown to induce avoidance in other Ambrosia beetle species, and in this way, the combination of both verbenone and methylsalicylate in Beetle Guard may offer increased repellency to target beetles. Recent studies from the ROD-Ent lab have shown that both products significantly reduce trap capture rates of ROD-associated species. However, it's necessary to verify that a repellent's ability to reduce trap capture also correlates to an ability to reduce actual tree attack. This same study also established that 100% ethanol is the most effective lure specifically for the ROD beetles. And this is really valuable in terms of integrating repellents with attractants in a push-pull strategy that is often most effective for protecting target areas from Ambrosia pests. And this is basically what it sounds like, where repellents push beetles away from high-value target areas, and attractants pull beetles in the same direction. So they're really two chemical signals coercing beetles in a certain way. So while an effective lure has been established, repellent efficacy has still not been fully determined. Due to the need to verify that repellents reduce actual tree attack and the need for alternative post-felling management treatments, the next logical step was to apply these compounds in more varied real-world management scenarios. It's for this reason, my research evaluated the efficacy of SPLAT Verb and SPLAT Beetle Guard for their ability to reduce beetle attack, colonization, and frass production when applied to infected ʻōhiʻa bolts as an alternate post-felling management approach. To do this, I conducted two 10-week trials that took place in the Waiakea Forest Reserve on the east side of Hawaiʻi Island. Trial 1 took place in the wet season and trial 2 in the dry season. The Waiakea Forest Reserve is a lowland music forest with ʻōhiʻa as the dominant canopy tree species. The site was further selected for its high ROD infestation and presence of all invasive ROD beetle species. Each trial included 18 ROD-positive ʻōhiʻa trees, which were felled, cut into 5 successive 1-meter bolts, debarked and placed into one pile per tree, pretty similar to how they would be in actual management scenarios. Bolt piles were clustered in 6 replicates of 3, wherein each of the 3 treatments were represented, which were 72 grams SPLAT Verb, 72 grams Beetle Guard, and an untreated control. And repellents were specifically dispensed as 18-gram dollops via a pre-calibrated caulking gun onto 4 plywood squares affixed to the corners of each bolt pile. Before treatment, previous beetle attack on all bolts were marked, and after treatment, new beetle attacks were counted every week for 10 weeks. After the field period, the largest bolt from each pile was halved, returned to the lab, and placed into rearing chambers to quantify beetle emergence and frass production, which was conducted for another 10 weeks. In terms of statistics, beetle attack was analyzed by fitting a generalized linear mix model, assuming a type 2 negative binomial distribution, which based on model diagnostics was most appropriate for the non-normal, over-dispersed, and zero-inflated count data that was being collected. Repellent treatment type, collection week, and the interaction were used as the predictors, and number of new beetle attacks was used as the response. Also, bolt replicate was nested within individual trees to account for repeated measures, and beetle emergence was also assessed with the type 2 negative binomial GLMM, whereas frass production was assessed with a Tweedy distribution GLMM, because frass production was not count data as opposed to the other components. Repellent treatment type was used as the predictor for both models, and number of beetles emerged or quantity of frass collected was used as the response respectively, while controlling for a week as a random effect to account for small-scale temporal variation in beetle activity. And overall, the results were very encouraging, particularly in the beetle attack assessment. On the left here, we see the attack results from trial 1, and on the right, the attack results from trial 2. The y-axis is mean new galleries per bolt per week, with the control group in blue, Verb in dark green, and Beetle Guard in light green, and the differing letters above each bar indicating a significant difference between groups based on the model results. As you can see, in both trials, beetle galleries were significantly reduced by both Verb and Beetle Guard compared to controls. Notably, in trial 1, Beetle Guard actually outperformed Verb, while no difference between repellents was observed in trial 2. So the attack results look really good, but there is still a question, which is why did Beetle Guard outperform Verb in one trial and not the other? And I think this could be attributed to a couple things, but primarily seasonality. As Ambrosia beetle community composition is typically dependent on species phenology. Since trial 1 was conducted in the wet season and trial 2 in the dry season, the 4 ROD-associated beetle species may have been active at different proportions between trials. And this is important because repellent efficacy can often be highly species specific. So if the community compositions differ between trials, we could reasonably expect repellent treatment effects to differ as well. Unfortunately, due to the nature of the experiment, it was not possible to determine which species were responsible for gallery formation in the field. However, based on many other studies also conducted at the Waiakea Forest Reserve, Xyloborus ferruginus and Xyloborhinus saxonii are consistently the most abundantly collected species collected from bolts and traps, respectively, which is in line with the rearing results, which I'll get to, in which only these 2 species were collected. While it's not possible to fully verify, this suggests that these species may have been the dominant agents in gallery formation throughout the experiment. Alternatively, the differing treatment effects between trials may simply be due to the lower sampling values of trial 2, which exhibited 38% less total attacks than trial 1. And this may also have just been a result of normal variation in seasonal beetle activity. And here are the same beetle attack results over time. Again, trial 1 on the left, trial 2 on the right, same treatment color scheme, and the y-axis is mean new galleries per bolt per week. In addition to treatment type, in both trials, sampling week was also found to be a significant factor determining the creation of new beetle galleries. New galleries decline over time, and the vast majority of new galleries were formed in the first 5 weeks of both trials. Specifically 91% in the first one and 78% in the second one. After which new beetle galleries gradually fall to near 0 by week 10 across all treatments. And this likely has to do with host suitability. Ambrosia beetles require particular environmental conditions within host trees in order to propagate their symbiotic fungi food source. And these conditions gradually become less suitable for this purpose as trees lose moisture, nutrients, and begin to decay, ultimately lessening beetle attractiveness. In another study conducted at the Waiakea Forest Reserve, rod beetles were found to attack standing ʻōhiʻa for an average of 288 days after initial rod infection and up to 351 days. The method of felling and bolting trees is meant in part to reduce habitable beetle and fungi substrate by accelerating this drying process. And the results from my project are in line with the observation that trees decline in attractiveness over time after death, and most notably that bolting trees likely hastens this process pretty considerably. I think this really puts into perspective how important quickly treating infected trees is, since bolting eliminated attack by week 10, as opposed to leaving trees standing where they can more readily retain these suitable host properties and be attacked for up to a year or beyond. Moving on from the beetle attack to the rearing and emergence results. As mentioned, 2 species were collected overall, but in trial 1, only 1 species was collected, which was Xyloborus ferruginus. Here we have the average ferruginus emergence per bolt per week from trial 1 on the left and trial 2 on the right. Again, control in blue, Verb dark green, Beetle Guard light green. And as you can see, repellents alter the emergence of this species differently between trials. In trial 1, ferruginus emergence was reduced by only Beetle Guard, whereas in trial 2, neither repellent reduced emergence of ferruginus compared to control. In trial 2, another species was collected, which was Xyloborhinus saxonii, and these are the emergence results of that species. But again, no difference in saxonii emergence was observed between treatments. Interestingly, not only was this species present in trial 2 and not 1, but actually outnumbered ferruginus overall in the second trial, which is going to be important. For Xyloborus ferruginus, the differing results may again be attributed to the lower sampling values of trial 2, which had 67% fewer total ferruginus collected than trial 1. which may not have been really suitable sampling values to observe treatment effect. Saxinii had similarly low sampling values, which could explain the lack of treatment for that species as well. However, repellent efficacy is often dose dependent, and in some studies, Saxinii repellency was found to require higher dosages of verbenone than those used in this experiment. So alternatively, the repellent dosages may have just not have been high enough to induce Saxinii repellency in a way that influenced emergence. Also, interestingly, 32% of total ferruginias collected in trial 1 originated from a single verbenone treated bolt over the course of 2 of the 10 collections. And in the same way, 85% of Saxinii in trial 2 originated from a single beetle guard treated bolt over the course of just 2 collections. And this is not too surprising, as I've found from my experience rearing rod beetles from bolts for the last 5 years, that the natural and stochastic variability of beetle tree attractiveness can often produce irregularities in sample collection, and a single highly productive bolt can easily obfuscate trends. This may have been the case in this experiment, as only 1 bolt half from each tree was able to be collected for rearing, and even that was pretty hard. And this just really highlights the need for robust sample sizes when assessing Ambrosia beetle colonization in future studies. Going back to the relevant figures, we can see this phenomenon represented graphically really well. Here's ferruginous emergence from trial 1 on the left, and Saxinii emergence from trial 2 on the right. And as we see, the 2 outlier collections from each trial make their respective treatment groups stand out much more than we expect. Lastly, moving on to the frass production results. Here we have the average milligrams of frass collected per bolt from trial 1 on the left and trial 2 on the right. In trial 1, the amount of frass collected was significantly reduced by both Verb and Beetle Guard to a similar degree compared to control. However, in trial 2, no differences in frass production were observed between treatments. But what's really important to note here is the scale of the y-axis between trials, as trial 2 produced average frass values around an order of magnitude lower than trial 1. Focusing on trial 1 for the moment, where we have very strong sampling values, we can see how the beetle attack results from trial 1 on the left pretty closely mirror the frass results from trial 1 on the right. And this is great because we can more confidently correlate a reduction in beetle attack with a reduction in frass production, which before this was generally just an assumption and not quite fully substantiated. Unfortunately, the same trend was not observed in trial 2, and this again could likely be attributed to the persistently lower beetle activity of the second trial. The total quantity of frass collected was 82% lower than in trial 1, which may have made observing significant treatment effects much more challenging. As before, these lower sampling values may be explained by species phenology. Flavorus ferruginus produces the greatest quantity of frass compared to the other rod-associated species. And in contrast with trial 1, where only ferruginus was collected, beetle rearing results suggest that Saxinii were significantly more active and in greater numbers than ferruginus in trial 2. And this may explain a reduction in frass production and lack of treatment effects. Alternatively, as mentioned, Saxinii has been observed to require higher repellent dosages than those used in this experiment. And so Saxinii frass production may simply be less affected by repellent treatments at these dosages. So to recap, here each check indicates a significant reduction for each component per trial. And as we see, verbenone reduced beetle gallery formations in both trials and displayed the capacity to reduce frass production, but not beetle emergence. Beetle Guard also reduced galleries in both trials, notably more than Verb in the first one, and exhibited the ability to reduce beetle emergence and frass production. As beetle attack and frass production are the primary concerns to inoculum dissemination, Both products show a strong potential for use as an alternative post-felling management solution to combat ROD. SPLAT Verb is currently registered for use by the EPA, and state registration in Hawaii is underway as well. And since SPLAT Verb may soon be accessible for use here in Hawaii, it would be prudent to anticipate its addition to the tools available to us to manage ROD. Beetle Guard, on the other hand, is currently only available under an experimental use permit, and as an unreleased product is neither registered under the EPA nor state agencies. So while Beetle Guard is further from being available for use here, it may be a moderate improvement over Verb, and so should similarly have attention paid to the progress of its approval status. In each trial of my experiment, new beetle attacks were bordering on 0 by week 10, and because both products have a manufacturer's recommended longevity of 4 months, a single application of either repellent may be sufficient for the extent of a felled tree's host suitability period. A 750 gram tube of SPLAT Verb is currently $120 and can be used to treat 10 trees at the dosages used in this experiment. So reducing inoculum production on a felled tree may simply cost $12 and be readily available to land managers and the public. I think it's hugely important, again, to emphasize how rapidly beetle attack reduced after bolting trees compared to leaving them standing. Really going to show how the importance of quickly identifying ROD infection cases and applying treatment methods as soon as possible to most effectively limit beetle contact. As we saw, some of the treatment effects seem very hindered by low sampling values and sample size. The time since infection for all the trees used in this experiment is unknown. And as beetle activity is highest surrounding the initial infection period, application of repellents on freshly infected bolts may yield higher sampling values and more consistent treatment effects. Because we also saw a lot of results that point to differing outcomes based on species, further studies on the compared efficacy of these repellent products would be useful in order to optimize an application strategy, explore more varied dosages, and more closely examine these species-specific effects. As mentioned, repellent efficacy could also be further optimized by pairing repellents with other semiochemical attractants in an integrated push-pull strategy that is broadly applied in the management of other Ambrosia beetle pests. Overall, ROD has proven to be a devastating forest pathogen in Hawaii for which few management strategies exist. Managing the Ambrosia beetles will likely pay dividends by limiting environmental inoculum and thereby reducing the rates of all infection pathways. Tarping can be an effective strategy to do this, but is not always feasible. And semiochemical repellents offer a vital management tool for when this is the case, with the added benefit of reducing inoculum production before it starts. Due to the product's accessibility and ease of use, the repellents may prove to be a valuable alternative post-felling management strategy that can be widely employed by land managers and the general public. More so, the results from this study can be used to inform the testing and application of these compounds in a broader range of ROD management scenarios, such as their application to standing infected and standing healthy ʻōhiʻa. Any restriction in the spread of ROD will have considerable positive impacts on ecosystem resilience, stability, and conservation in Hawaii, and beetle repellents increasingly seem like they will play a pivotal role in the multifaceted management approach that is needed to manage the disease. The findings from this project support the growing body of evidence surrounding the use of semiochemical repellents within the ROD pathosystem in efforts to cut off infection at its source, restrict the spread and severity of ROD, and preserve the ʻōhiʻa forests that make Hawaii home to all of us. And with that, I would like to give a big mahalo to my entire thesis committee, Advisor Patrick Hart, committee members Kyle Roy and Ryan Karoy, the whole ROD entomology lab, past, present, and future, the RCUH and USGS, JB Friday at the Komohana Research Extension Center for providing lab space for us for so long. Whole TCBES committee, of course, and the whole program has been great. Sad to see it go, but I'm excited. Basic, of course, for never hesitating to help me drag bolts out of the field or anything else we ever asked them to do. And the Forest Service STD grant for giving me a little chunk. So that, everyone. Any questions? I don't know how this works.
So you can see this question. There's a lot of people online. I think you can look at the chat. See if this question's there. Yeah. Popular.
Yeah, Becky.
Thanks to you, that was a really nice document to see sort of up together. I was just wondering about the push-pull strategy. When you have a tree like that's very dense, that didn't work because there's so many trees around. How are you going to root them from the tree?
Oh, well, I guess that's
if you can repeat the question. I'm not sure how well we.
okay. Yeah.
I'm
So
not sure.
Becky asked how well push-pull strategies work. I assume in like a dense ʻōhiʻa forest where there's a lot of trees around. So the push-pull would more be applied to like a whole forest-sized system. To say like, oh, this is a preserve we really want to protect. So we'll apply repellents to all these trees, you know, standing infected or healthy ones to draw beetles out into just an area of like less value that's not managed or something like that, but not really as applicable to like single trees in an otherwise unaffected forest. Find the chat.
I was wondering, did you see for repellents and flores, did you see any effect on other communities of other insects?
Yeah, so the question is, did I see any effect on other species when looking at the effect of repellents and lures? And not really, no. For the repellents in my study, you know, we're just looking specifically at beetle attacks, so don't really get a good gauge on anything else, but they are pretty bark beetle specific. So we wouldn't really expect something like that. For the lure stuff we've done before, again, we really didn't get too high of a trap capture for like a bycatch. So it didn't seem like those were really having a big impact on anything else, which is great, exactly why we don't want to use insecticide, pretty bark beetle specific.
At least a couple of questions there.
Yeah. So let's go up.
Just one from Rob Hawk.
Okay, so one question is, how do your results compare to applications against bark beetles like mountain pine beetle, similarly effective? I can't remember the results of the mountain pine beetle offhand, but I'm pretty sure this is like a lot of this is based off that species where these compounds are used for the mountain pine beetle. So I can't really compare the specifics, but they both seem to be affected by the repellents in like by reducing them. Yeah, no.
Tio, you said that like you could potentially, you know, with SPLAT Verb, create a repellent for a tree for as cheap as $1. But I was wondering, you know, how much area does that kind of repellent cover? Like, is that one application? If you have an extra large ʻōhiʻa that you can't fell, would you need to apply like multiple applications? Is there any sort of kind of swath width of how wide the repellent works?
Yeah, that's a really great question. I think that's still kind of being determined. It's going to be pretty specific based on location, you know, with like how humid it is here, or just other weather factors, and how that volatile plume kind of acts. But the manufacturer's recommendation is those like pretty much the same 4 dollops on the bolts per tree. So we would expect each tree to need a treatment. And I think we're still figuring out, bark beetles attack the whole length of the tree. So we still kind of need to determine, it works for this project, since the bolts are all pretty clustered in an area, but is that plume reaching the top of trees for the standing ones? Yeah, does that answer your question?
I think so. I have a second related question.
Yeah.
Do you see SPLAT Verb or the other one being potentially like landscape level applied? Like, or would there be problems with that, like with only falling on the canopy or something like that?
Only falling on the canopy?
Like if you were to like aerially broadcast
Oh,
SPLAT Verb.
yeah, that's a great question. I don't really know much about like there's a lot of different methods to dispense the repellents. They can come in like little pouches that you can put out, but those aren't as ideal because like part of the point is to reduce litter in the environment. So putting one out, wouldn't be great. You'd have to have people go out and collect it, whereas with the repellents, they naturally biodegrade. So you can just put one thing on and leave it. Yeah, I'm not sure if like aerial kind of stuff has been used yet, but I think it could work on a landscape level. Yeah, I'm not completely sure. I think it depends on like, are you putting on felled bolted trees, standing trees? I think there's a lot of questions still left to be answered.
You got to answer Rob Hopp's question.
Okay, yeah.
Okay. So why do you suppose beetle attack is reduced so quickly by felling and bucking logs opposed to leaving them standing?
Yeah, also great question. Basically, bolting helps accelerate the wood drying process, and the beetles need trees to be like moist and full of nutrients to propagate their fungi on which they feed. And so by bolting a tree, you're just breaking the surface area for it to be exposed to the sun and the elements and dry out and just become less habitable to beetles. So they're much more likely to attack standing trees, which hold on to these properties a lot longer than bolting.
Bolting, removing the bark, or is it cutting it into sections?
Yeah, bolting is cutting it into sections. The only reason bark was removed for my experiment, which is decently more labor intensive, is just to look at those beetle attacks confidently. Just because you can imagine on a tree with a bunch of bark, especially in ʻōhiʻa with all kinds of crazy qualities to it, it's going to be pretty much impossible. So that does make this not as completely comparable to felling trees normally, unless someone wants to spend a lot more time to debark them. But I think the comparison still stands. Yeah.
The question's relating to that, because that's gonna open up the canopy more light and probably bring in weeds. How do the beetles do when they're in higher light conditions? Are they typically higher light or temperature?
I'm not really sure. Yeah, I think UV composition in Hawaii has still not been like really fully, investigated. But with rod trees losing their entire canopy, I don't know if there is going to be a difference in the amount of light and sun that's getting in. A snag with no leaves compared to a felled tree. So I think like pretty comparable. Do you have any other questions?
From Lisa.
Is that at the bottom? Yeah. Okay, question. Do you think that the current recommendation rates of SPLAT Verb will need to be refined for the ʻōhiʻa system? If so, how would an experiment like that be designed? I think that's a great question. We read SPLAT Verb. So I'm assuming you're talking about the dosages, Angel. And yeah, that's a great question. There's a lot of experiment brings up related to dosage. And there's previous studies that have been done by Roy that have looked specifically at known dosages that have found, Saxinii requires high repellent dosages. And yeah, so I think we can draw a lot based on of what Kyle has worked on, but the dosaging is still, the jury's out with beetle guards. That hasn't been looked at. But yeah, basically you would apply, you'd have different groups of varying dosages and look at some metric of beetle activity. This project looked at beetle attack, but you could also use, sticky cards to look at beetle visitation, frass production again, just different things to see how the beetles are affected. We got one from Lisa. Maybe you mentioned that your field experiment you used deep bark logs. Would you expect similar results in logs in bark? That is a really good question. I would expect pretty similar treatment effects, like proportional treatment effects, but I think that potentially leaving bark on would allow the bolts to retain some of the host stability properties that we were discussing for a bit longer. Yeah, the beetles really seem to like nooks and crannies. So I think similar proportional treatment effects, but maybe a little different in terms of like duration of attack or something like that. But that'd also be a great experiment to look at, moisture content and that kind of things on debarked compared to intact logs. Yeah, exactly.
So I don't know much about the background on it. So do you think that what you found, kind of these two methods that you use, these are worth continuing moving forward, or are there other alternative options you guys are thinking that need to be tried before we decide this is a good route, let's keep going with this, and this could be the answer?
Like repellents versus something else, or different repellents?
Yeah, like the two you used, right? So like based on the results you saw, is just like, let's continue with these two, these are the best we think, or is there another one like we should still try this one?
Yeah, there are some different semiochemical compounds, but I think these are two of the most obvious ones and researched ones that seem to be pretty consistently effective in other species. So I think definitely worth continuing with these. There's definitely not too many other options. They're, I'm not super familiar with the other ones, but there might be a couple. But yeah, these ones seem kind of like the front runners.
Yeah, I mean, based on what you saw, it seems really encouraging, especially that you're saying it's not even effective in the other species.
Yeah.
That's pretty.
Yeah, absolutely.
Yeah, and your photos are amazing. Like, it's beautiful. Like, it's really gorgeous. But beyond that, I guess it's a question. It's just for me to think about the life cycle of the beetles or such. So all of the bolts that were included in the study had already been hit by beetle attacks prior to doing treatment. Is that correct?
Yeah.
And then for the ones which were treated, how long you left them out there for a while after they were treated, and then you brought them into the lab, right?
Yeah.
And was it you left them out there long enough that any beetles that had already attacked the logs would have kind of worked themselves out? And so what you saw in the lab results were only from what could potentially be post attacks from the treatment being applied? Is that correct? Is that
pretty much. We've seen a lot of variability in how and when a bolt will start producing, beetles and frass and everything. This would definitely probably be considered like the tail end. And that's definitely something that could be investigated more thoroughly. In addition to using more fresh trees, taking a bolt in like the middle of a study or the very beginning would be super valuable to probably get better results on beetle improvements and frass. For sure.
And is there any way to answer this right now? You had a few logs that were like super producers, right? And they're just like pumping it out, right? Is there any way to predict or characterize which ones those might be? Like, what is it about that tree or that situation that made them so
Yeah, there might be, we've looked at like moisture content, I think that might be one of like the only metrics, definitely height on the tree is a factor, the different species, there's whole different, graphs of what height beetles like. And yeah, I don't think it's been fully determined, certain species like certain heights. But yeah, I think a lot of the data have been not super definitive in terms of like moisture, with beetles, like it's not as nice of a correlation as we'd like. But I think that's a great perspective, future study on looking at more varied qualities of both for sure.
And I have one.
Yeah.
I have more of it. So for beetle attacks, you showed a sort of a time series curve, right? But you didn't show that for your other two, the
Right.
frass production and I'm curious why or
Yeah, so one being frass production, there were only 2 collections at the halfway point in the end.
Okay.
And that's just because we've tried to do frass collection before and it's pretty difficult, I decided to do it because it's a lot easier to just let frass accumulate and you can like kind of better, collect it.
that makes perfect
Yeah,
sense.
and so, a two collection time points would really be valuable. But also I did do that, with like beetle emergence, and it's super non-linear, like compared to this, where it's like, okay, I clearly see what's happening. Beetle emergence was like, you'll take them back to the lab and they'll just sit for weeks. And then all of a sudden it's like, beetles, and then it'll drop off to nothing. And then maybe another like, beetles. So I think I looked at week as a determining factor for those and it just wasn't significant. It's a lot more just random. Think about.
And I think that relates back to my original question is that the beetles that are emerging, are they emerging from attacks prior to the treatment or are they all mostly post-treatment emergences? And I
Great
don't-
question. I don't think I have a definitive answer, but I think it's totally possible that they come from like previous attacks before the experiment started. I think it's still a useful metric because maybe the repellents are influencing those beetles that came before, because that's how it will be in actual management cases. There'll already be beetles there, so maybe it will help push them out, make them leave. So.
Okay.
Yeah, that's the value of having a control.
Yeah.
There's 2 more questions online, but also.
I'll
Stay
say
for a long time.
That's a good sign.
Stop this whenever you want.
We can, I'll ask the rest of my questions.
Okay.
There's one from Hilo.
Where is it? Is that it? Another question, do you see an application for SPLAT or Beetle Guard where large scale logging or Ambrosia treatments take place here, as those kind of events could potentially inflate beetle populations in an area where ʻōhiʻa ROD exists? Yeah, I haven't really considered their application on kind of logging systems. But yeah, I could definitely see that, being useful, if you have like a logging plot and around it is still intact forest, maybe there's gonna be a bunch more beetles leaving those trees that were felled. And maybe you could do the push-pull strategy where you have repellents on that perimeter and lures in the middle of the logging to kind of draw them away from that area that you want to protect. Yeah, I think there's definitely a path for using systems like that. Question. Get this on, persuaded.
Oh, sure enough.
Okay. Was there another one?
Well, yeah, so I guess Hilo had 2 questions, but his other one was, he was curious about the total number of beetles that emerged from each 10-week trial. It seems like some cases, 1 beetle per week resulted in 200 milligrams of frass.
Yeah, to those. Beetle emergent results. Yeah, so I believe in the first trial, we had around 60 total beetles collected over that 10-week period. And yeah, you can see Beetle Guard had like almost no beetles emerge. And yeah, as I discussed, like 30-some% of collected ferruginous came from one bolt over 2 collections. So these data could definitely be a little stronger. And I think that's why we see inconsistent treatment effects. And in the second trial, I think there were about half as many ferruginous, like that was like 67% less ferruginous. Yeah. Yeah, it's quite a reduction. And then Saxinii in the second trial was about 34. So I think second trial ferruginous was 32, Saxinii was like 34. So yeah, quite a reduction in beetle activity. So that answer that? What was the
There's not that, I think you're exhausted. Yeah, he was just saying that there was hardly any beetles, but there was lots of frass being produced.
Oh, yeah, yeah, exactly, and that could be a result of there being way more Saxinii because they produce significantly less frass than ferruginous. So even though there's like equal or more beetles in the second trial, we see way less frass because it's a different species that's probably contributing, producing that much frass. Yeah.
So if, maybe I missed it, maybe you addressed this, but did you not collect any of the other ROD-associated beetles, or did you just kind of analyze Saxinii and ferruginous because they were the only ones you caught in the
No, would have loved to get more diverse species for sure. But yeah, ferruginous and Saxinii were the only ones collected. And that's pretty typical of this field site. Even though there are those other species, we get them in traps, we get them on sticky cards and all these things. Typically, or maybe have never gotten perfrints and affinis from bolts from that site. So yeah, I don't know if they're just in like a far less proportion. Yeah. Sometimes they're just a couple compared to hundreds of Saxinii. I think in a recent study, there were actually like a ton of them. So it's interesting that we're not getting them from bolts. Maybe the sample size wasn't enough. Maybe it's just different areas of the reserve. But yeah, still a lot of unknowns about community composition.
Thank you so much.
I think that's it.
Yeah, big round.
Thanks everyone. Thanks for coming on Zoom.